Log on, tune in, find out. Another good idea from Cambridge.
But before we begin that, this quick announcement. There will be a small drinks reception this evening at 4:30 with wine and bits of cheese and olives. Because we're sort of got that Mediterranean weather going, so let's really try and pretend there's some sunshine, etc. So it'll be 4:30 upstairs, where the blackboards and coffee normally is. And I think that's it on this.
Thank you very much. I would like to start by thanking the organizers for the kind invitation to spend some time here in Cambridge and to give me the opportunity to talk. So I want to talk about BPS invariants of rational surfaces. So just in brief, to give you an idea what are the BPS invariants, they are essentially the Euler numbers Euler numbers of instanton moduli spaces. Spaces and computed using n equals 4 UR Yang-Mills theory. Wrapped on the rational surfaces S, which include the Hirzebruch surfaces and all the blow-ups of the Hirzebruch surfaces. And let me start with just a brief motivation. One motivation was actually very nicely discussed by Steven van Doren in this talk, is actually the physics in orthogonal dimensions. So to this end we take a bundle of the canonical bundle of the rational surface over the surface, and if we want to do M theory, there will be an M theory circle, and then there is the space-time for dimensions. And now all the systems of say M5 branes wrapping the surface and the M theory circle and direction in space-time, or D4 branes into A theory, where the D4 branes wrap space-time times a line in R4, or the D3 brane instantons, which just wrap the surface, are all expected to have in some way or another their corrections to the space-time theory will be involve the Euler numbers of these instanton moduli spaces. And the computations of these Euler numbers also gives insight, in the case of the M5 brane, into the difficult 0,4 SCFT. And it arises from the reduction of the degrees of freedom from S to 2 dimensions. Okay. So that's briefly one motivation. Another motivation is as a toy model for black hole physics. And in that case, the line bundle over the surface will be a compact Calabi-Yau, and then one gets the famous MSW black holes. And in this is actually this is a toy model of that system, which is also very hard to get a handle on. And the third motivation is n equals 4 super Yang-Mills itself. And I would like to give a bit more detail about this motivation, which is especially the link with S-duality, as discussed in the Waffa-Witten paper from 1994. So here the starting point is very similar as in the talk of Lotte Hollands and Vasily Pestin. I wrote this down already. So we start We have the path integral of Young-Mills theory. You have a path integral over some scalars, the gauge fields, and some fermions, e to the minus s. And Waffa and Witten showed in '94 that this supersymmetric path integral localizes on the instanton solutions. So on the solutions where f is equal to minus star f. And let me just give you the famous action for the gauge field is 1 divided by g squared integral over the surface trace f at star f minus I theta divided by 8 pi squared and trace f at f. Now for the instanton solutions, this specializes to tau times say kappa, where tau is the one I don't think I wrote this down. This just proportional. This theta divided by 8 pi squared plus I divided by g squared. Maybe there's a 2 pi here and this is 4 pi. And therefore the path integral takes the following form. It is a sum over the instanton numbers kappa. The instanton number is this quantity. Euler number of the instanton moduli space. R, kappa q to the power kappa.
Can you remind me, was that n equals 4, or was it the twist? Wasn't it the twisted thing?
Yeah, okay, I forgot to mention. So they use, they topologically twist the theory, and then they show that that it localizes on the instanton solutions, and that you get the Euler numbers of the moduli space.
Yes. So I just want to be clear. So is the topology twisted thing which localizes? If you don't do the twist, does it localize? It doesn't localize the same way, or does it not matter about the twisting? Because of the curvature of the surfaces, you need to twist in order to preserve fermionic symmetries. So there would be no symmetry preserved if they're on a curved space. So the non-twisted theory would not localize. So, yeah.
Okay. Now the S duality, which goes back to the 70s, is essentially a replacement of f with star f and tau with minus 1 divided by tau, and this implies for these generating functions of the Euler number modular properties. So it is expected that R of tau would be in some sense would be closely related to R of minus 1 divided by tau. So these functions will have modular properties was the conjecture. And that
Is your normalization is theta periodic mod 2 pi or 4 pi?
It should be mod 4 pi. Yeah.
Okay.
Tau to tau plus 1 should be this should be more or less invariant under tau to tau plus 1. And these functions turn out to be actually vector valued modular forms, because you can turn on certain het hoofdfluxes, say mu, and then the S duality it transforms the different het hoofdfluxes among each other. And there is also a modular weight which you can also work out precisely. Now for these rational surfaces, Waffa and Witten used results from the mathematics literature, and in particular for RS1 they found that H is actually a modular form. Later in the talk I will give the precise expression. For RS2 they found what is in modern language a mock modular form, or mixed mock modular form. And the mathematicians had no results for higher rank. So that was my main motivation to compute these Euler numbers for higher rank gauge groups on these rational surfaces. So in this talk I will explain how to compute essentially these numbers for higher rank gauge group, but the question about modularity I will leave for a future talk. So let me briefly give the outline of the talk. First I will give some more information about the rational surfaces. Then a couple comments of the relation between instantons and sheaves. Then we get to the mathematical aspects about so-called Hardenauer-Simon filtrations and wall crossing. And if I have time I will discuss a little bit the modularity for rank 1 and rank 2. Okay. So start with the rational surfaces. I'll start with the so-called Hirzebruch surfaces, which are a vibration indexed by this integer L over a base curve C, which is isomorphic to P1. And the fiber of the vibration is also isomorphic to P1. And these are the only two cycles of the rational surface. The intersection numbers are given as follows: C squared is equal to minus L, C dot F is equal to 1, and F squared does not intersect, is equal to 0. The so-called canonical class is given by minus 2 times C and minus 2 plus L times F. And typically later we'll see for stability we'll use a polarization J, which takes its values in an ample cone, which I denote by C say of sigma L. And it is convenient to parameterize it in the following way: the two-dimensional lattice of the two-dimensional homology is parameterized. One direction is F, and the other direction is C plus L times F. And then the ample cone is this quadrant of the space. Okay, then then all the other rational surfaces are obtained essentially from blowing up points in the sigma L, in the Hirzebruch surface, except for, and the projective plane itself is obtained from the blowing down one point of the Hirzebruch surface with L is equal to 1. So it is, so if phi is the blow up map, then this is, so the projective plane is a 1 point blow up of the Hirzebruch surface with L is equal to 1. And for L is equal to 0, we get just P1 times P1, which is often used in discussions about geometric engineering, etc. And also played a big role in the talk by Steven van Doorn. Let me see. Okay, this was everything I wanted to say about the surfaces. This one should not go up. Okay, so in the present context, it's hard to, or it is unknown how to compute this integral using supersymmetric localization techniques. If you do it, you just, well, Buffer-Witten showed that the localization gives f is minus star f, and then you are basically stuck with an algebraic problem how to, which it's hard to proceed. So yeah, we use we translate the instanton bundles to vector bundles, and then we use the mathematics to actually compute the numbers. So the vector bundle will have rank equal to r. That's the same. The first Turing class is given by I divided by 2 pi times the trace over the field strength, and the Turing character, the second Turing character, is equal, of course, to half C1 squared minus C2, is given is essentially the instanton number. The trace of FHF. So I usually denote these three quantities by a vector gamma, which is r, comma, C1, comma, C2. And another combination of these Turing classes, which often appears, is the so-called discriminant, and it's given in the following way. It is 1 divided by r times C2 minus r minus 1 divided by 2r C1 squared. The main theorem which relates the instantons to vector bundles is the so-called Donaldson-Uhlenbeck-Yau theorem, which states that irreducible anti-self-dual connections. So anti-self-dual is just f is minus star f, are in one-to-one correspondence with equivalence classes of stable holomorphic vector bundles. And then if they are reducible, then you get these the bundles which are polystable but not stable.
What's the next step that localizes on self-dual versus anti-self-dual, or instantons versus anti-instantons?
It is
Is it a property of the surface?
related to the question that people ask you in your talk, right? Because it's related to the number of self-dual cycles versus anti-self-dual cycles.
It does not come from the signature.
Yeah, the signature. Yeah, you have a signature which is 1, comma, say B2 minus 1. And then you can have one self-dual form and the other are anti-self-dual form. So like for R4 it doesn't matter, but for these surfaces it matters whether you take self-dual and self-dual.
I was wondering what the meaning of the discriminant is. Is there some quadratic form that you make out of gamma that this is the determinant of, or what do you think of that?
Yeah, you can write this as say 1 divided by R, then the second term character, minus 1 or plus 1 divided by R C1 squared. And yeah, you see this quantity actually showing up a lot in papers on MSW, CFT, and so that this is how to say that.
Well, it looks like you could make a quadratic form that has entries C1 on the off diagonal and C2 or something involving R on the diagonal. Is that quadratic form play some natural role in theory?
This quantity plays a natural role. That if there's a symmetry which I was going to discuss, which is tensoring by a line bundle. If you tensor a vector bundle by a line bundle, then the C1 and C2 change, but the delta is unchanged, and the moduli space is also not changed. So you have an isomorphism of vector bundles, which is just tensoring by a line bundle, and this delta is unchanged by that. So C2 will be shifted by a quantity. It involves also C1 squared, and then.
It sounds kind of reminiscent of the elliptic transformation of Jacobi form.
Yeah, exactly. That's this quantity. So you can usually I will not sum over the C1s because that would just that's the theta function decomposition. You can So let me. So there's the. So if I have a vector bundle F and I tensor it with a line bundle L, which has first term class C1 is equal to K, then this one will have first term class C1 plus K. And because there's an isomorphism, I only have to, or there's actually an R here, I only have to sum over C1 modulo R. And this isomorphism precisely leads to a theta function decomposition in the protection function. Any more questions? Okay, then for these higher dimensional spaces, vector bundles are not really good enough because the instanton can be squeezed to zero size, and to take those into account, we will look at so-called coherent sheaves. But if you're unfamiliar with them, just think of it as vector bundles. Then the notion of stability. I will use so-called Giesecke stability. It is a refinement of mu stability. And this is defined in the following way. First one chooses a J in this ample cone C of S. And one defines the following polynomial, which is called Hilbert polynomial. It is a polynomial in N for a vector bundle F. The first term does not depend on F. Then the second term is C1 F dot J divided by the rank of F times a linear power of N. And then there is a bit slightly lengthy expression of order 0 in N. It's C1 F squared minus KS dot C1 F divided by 2 minus the C2 of F. And now the definition of stability is that a sheet F is D-square stable if for every subsheet there's F prime in F, the polynomial for F prime is smaller in some sense as a page of the polynomial for F. And what this finally smaller means is that you first compare the highest power in N, then you compare the linear, if they are equal, and in this case they are always equal, you compare the linear power in N, and so this would be mu stability. If they happen to be equal, then you compare the zeroth power in N. So therefore it's a refinement of the mu stability.
So the arrows up and down here, this is the ones that you were done. For Giesecke stability, you know that if you have an anti-self-proof connection, then it is Giesecke stable, but not the other way.
Yeah.
It is possible to be Giesecke stable, but not satisfy Hermitian rules. How do you filter that out, or is that the right notion to?
Well, yeah, I think this notion is I think developed to have to build good moduli spaces and good invariants. And this is this stability indeed is typically mu stability. And
I'm asking about the connection to the differential equations that you have in the effective theory. So for points in, if you have the whole moduli space of Giesecke stable objects, that not all points in that moduli space will solve your equations in those. But maybe you don't care for specific reasons.
No, I haven't studied the differential equations so much. I think it is there's more a question of constructing the right moduli spaces and getting good invariants, and I would think it might be something that on the quantum level or so, whatever that means. This is a more refined notion, and I haven't tried to make this precise for the differential equations. Okay, so and in physics usually you have stability in terms of central charges, and then this stability condition basically appears as in the large volume limit. So this J can be seen as a Kähler modulus, and in the large volume limit you will just compare the different powers. Also, now we have, if the stability condition, we have a good notion of the moduli space, essentially, and in particular, what is useful is that there's a formula for the dimension of the moduli space of stable sheaves. This is given in the following, by the following formula. It's 2 times r squared times delta minus r squared chi of the structure sheaf plus 1. Now, if it is possible, this is a good space if so-called stable is not equal to semi-stable. Semi-stable is if there is if there is an equal sign here, and it, for example, happens if gamma is, for example, 2,0,0. If you can divide it by an integer which is bigger than 1. And then the moduli space will typically be non-compact, and you can compactify it, but then it still has singularities. So then the modern language to describe these spaces are stacks, and it becomes pretty abstract. But this dimension is still hot. That holds also for semi-stable sheaves. Okay, let me then define or give an idea of the BPS invariants in this language. BPS invariants plus their generating functions. So let P x comma w. This is now a Poincare polynomial. So hope it's not too confusing that the subscript j distinguishes them. This is the Poincare polynomial. This is defined by I is 0 to 2 times the complex dimension of x, and then enumerates the Betti numbers of the manifold x. And then the BPS invariant I define as w minus the dimension and then there's a factor at the bottom times the Poincare polynomial of the moduli space of the vector bundle. So in particular, I will do something more refined than the Euler numbers. I will look at the Betti numbers. Since the moduli space is compact and oriented, the Poincare polynomial will have a symmetry w to w minus 1 by Poincare duality. Now we have multiplied by this factor. And this symmetry you can see from physics, from the orthogonal dimensions, since the BPS index will be enumerate SU2 rotation characters of the rotation group in the space-time. Yeah, then I think this factor physically comes out of a sum over oscillators, and mathematically it are the automorphisms of the sheaves, which are in general for these stable sheaves. It's just a multiplication by C star. And basically, if you look at modular generating functions, then it are not these invariants which lead to the generating function with good modular properties. It are so-called multi-cover invariants, which also often appear in instanton computations. So I will distinguish those with a bar from the integer invariants. It is a sum over all the integers which divide the total charge gamma, 1 divided by m, and then omega gamma divided by m minus w to the power m times k. So if you so you get the Euler numbers by first multiplying this by this factor and then taking the w to minus 1 limit, and yeah, you see that you always get a minus 1 if you have this factor like this.
Is there a path integral description for young mills in which you do localization and then you need the Betty numbers?
No, there are no localization. It is not known how to get the Betty numbers using localization. I think it is it's an open problem. Okay, and then the generating functions are defined in the following way. I keep fixed the rank and the first chunk class. Then it is depend on z and tau. Z is just the exponent of w, just e to the 2 pi I z, and q is of course e to the 2 pi I tau. Then of course it depends on the surface S, and in general due to Warcrossing, also on the polarization J. It's a sum over the second chunk classes, omega bar, comma, W, J, Q times R, delta of gamma, minus R times the Euler number of the surface divided by 24. And okay, so that is the definition of the generating function. Then, so in the rest of the talk I will compute these generating functions for increasing rank. Now for rank 1 there's a general result for any Kähler algebraic surface S. And it's due to Kutze. Depends on S. It does not depend on J because you cannot, the rank 1 bundle cannot split into smaller bundles. And it's just given by I divided by theta 1 2 times Z comma tau. This is the antisymmetric theta function times the theta power of the eta function. And also in this case it does not depend on C1 because it is it will be modulo 1 in this case. So for higher rank, it is a difficult problem how to compute these functions, and therefore I specialize to these Hitzbrook surfaces. And it's mainly because then you can restrict to the vector bundles to these P1s, and a lot is known about the vector bundles over P1. So if you have a sheaf F and you restrict it to the fiber, then you will get a vector bundle whose rank and degree are given by the rank from the original sheaf, and the degree is given by C1 dot F. Now there is an old theorem that says that there are no stable bundles on AP1, and this basically says that omega of gamma I will explain this J epsilon comma 1 in a moment, is equal to 0 if C1 dot F is not equal to 0 modulo R. So this means I drew the ample cone CS, and the vertical axis is the fiber class, and horizontally that's something like C plus L times F. And Now close to the fiber class, if we go an epsilon away from this, epsilon and 1, then all the stable bundles will be also must be stable bundles on P1. But since they don't exist, so there will also be no stable sheaves or bundles on the total surface. And therefore, you can basically from wall crossing, you can get it now in all the other chambers, and then you can blow up and blow down if you want to go to P2 to get the other invariants. So somehow the real problem is, okay, this is a bit too fast, because since if you start crossing walls, you might also cross walls where you have C1.f is equal to 0 modulo R. So somehow the hard problem is what are the invariants for C1 is C1.f is 0 modulo R. So what if C1.f is 0? And for this I have a conjectured formula which I hope it will be proven. It takes the following form. It does not yet give them the numbers on the nodes, but I will explain what to do with it to get the BPS invariant. So I define the following generating function, minus 1 to the power r minus 1, with tau to the power 2r minus 3, divided by theta 1 2z squared, and then all the way to theta 1 of 2 r minus 1 times z squared, and then the last one will just be a single power, theta 1 to rz. And note, for r is equal to 1, you just get back the result for rank 1. So this is somehow the BPS invariant of the moduli space of sheaves whose restriction to the fiber is semi-stable. And so this is not a good invariant, because you see this has high order poles in W, because every theta function will contribute a pole, and here we have just a single order pole. So what we need to do is that this function should be, morally speaking, is the generating function on the boundary of the ample cone, which is not a good point to be at. We need to go an epsilon into the ample cone, and then in this process, a number of sheaves which are counted in this generating function we need to subtract from this function. And this procedure was done for the rank is equal to 2, and the C1 is equal to F by Yoshioka. And yeah, for the higher rank, yeah, I have conjectured this formula. So let me tell you how to subtract the unstable sheaves from that formula. This uses the mathematical tool of so-called Hardenauer-Simon filtrations. Hardenauer-Simon filtration. So the definition is that this is a filtration starts with just 0 and then F1 in F2 all the way to FL is equal to f, so it is a filtration of f, and it is such that the quotients ei, which are defined by fi quotiented by fi plus 1, or fi minus 1, are semi-stable. And the condition is that Pj, so this is the polynomial which appears in the stability condition of ei, comma n must be bigger than the polynomial of the second one in the list. So in particular, if L is bigger than 1, then F will never be stable, because this basically tells you how it decomposes in because it is unstable and how it decomposes in sub-objects. Now one can associate two sets of filtration an invariant which in some sense counts these filtrations, which I will define in the following way. So I let gamma of I is the charge vector of ei, and for such a filtration where all the quotients will have this charge gamma I get some power of W, then there is a sum I smaller j mu I minus mu j dot the canonical class, which I gave a while ago, times r I rj. And then there is a product over I L, and then these rational invariants omega bar gamma I W of j. And so using this Hardenauer-Simon filtration, one can now recursively start subtracting from that formula the contributions of the unstable sheaves, and this is very analogous to the Hardenauer-Simon recursion, which was first worked out for quivers and for vector bundles by Hardenauer-Simon and Atiyah and Bott. And actually, it are precisely these W powers which are in the mathematical literature sometimes associated now with BPS algebra. So you will make you associate to this charge as a Lie algebra element, which whose commutators precisely get these W powers. Okay, so let me just give you an example. H2 comma F. Z comma tau j epsilon comma 1 is this function upon the board, hc of tau comma f plus w squared 1 minus w to the fourth times the generating function of rank 1 squared. And yeah, you can, if you expand this function, you can check that the length of the Poincare polynomials precisely are given by this function. And another example is if this will be 0, then it's actually a bit more subtle, and it's actually you would need to define a refinement of the Hardenauer-Simon extension. This vector will become 1 divided by 1 minus w to the 4 minus 1/2. And so this prescription is recursive because you would need to first determine these coefficients omega bar of the lower rank and then work recursively to higher rank. But for vector bundles, the recursion is solved by Donzaguier in 1996. And in this context, you can basically apply the same recursion also directly. So you can express for higher rank here, you can directly express it in terms of a linear combination of these functions. Of, yeah, not linear combination, but yeah, terms which just in terms of these functions. Okay. So now we have, once you have the invariance here, you can start with the Walker-Smith formulas of Konzevitz and Sobelman and Joyce and Song in principle. You can compute the spectrum in all the other chambers. And this precisely matches actually this story of Hardenauer-Simon filtrations, because if you change your stability parameter J, then some of these filtrations will stabilize and others will, some of them will become stable and others will become unstable, and those are precisely the changes in the spectrum of the gauge theory. Okay, so how many minutes do I have left? 10 minutes? Okay.
Was it possible to predict the Mach modularity for higher rank sort of a priori without doing the computation?
No, it's, yeah, so I was slowly getting to the modularity part. It is, maybe you can you ask a question?
Sure.
Like, is it? So if the rank of the sheaf is equal to 2, there is some wall crossing, and the way how to take this into account in the generating function, it will be a bit a long function, but let me give it anyway. Please ask me any questions about unknown terms. So I will start with the function close to the boundary of the ample cone, tau j epsilon comma 1, and then the term due to wall crossing is it's a sum essentially over Chern classes of the components. So rank 2 can split into 2 components of with rank 1. So both gamma 1 and gamma 2 have rank 1. Then the sum of the Chern classes needs to be equal to the total Chern class of the rank 2 bundle. Then whether you have crossed the wall or not is determined by the following factor. So this is the term j is the term where we determine the generating function, and then we subtract all the terms from where we started. So this factor determines whether we cross the wall or not. If the sign of this one is the same as this one, then we did not cross a wall. And if the sign is different, then we did cross a wall. Now we multiply this by basically the degrees of freedom associated to the bound state in physics language. So that takes the following form. This is equal to 1 in this case. This is C1 minus C2 dot KL. So this is multiplied with the canonical class minus C1 minus C2 dot KL. And then there is a contribution in the exponent of Q. Sorry, this should be 1, comma 1, the first Chern class of object 1, the first Chern class of object 2. So there's 1, comma 1 and 1, comma 2. C 1, comma 1 minus C 1, comma 2 squared. And then you just have the generating functions of the rank 1 sheaves. And so you see this one has 2 poles. but because this one also has a 0, you precisely get a polynomial in W out of this. This one has a factor W minus 1 squared. So one of them will kind of make this one finite, and the other one is there by definition. And now this quadratic form here is an indefinite quadratic form, so you have to be worried about the convergence of the sum. But the sum is actually convergent, and it was precisely, this is precisely the context where Götze and Saguier started these so-called indefinite theta functions. Götze and Saguier. So they studied this, holomorphic sums over an indefinite lattice, and it happens that this stability condition, or that this condition precisely sums over positive cones in the positive definite sublattice. So if this cone is positive definite, and this cone is positive definite, and this is negative, and this is negative, then this condition says precisely that you are summing over positive cones in the positive definite sublattice. And if you change your polarization J, you are just changing the boundary of the cone, and you will add additional lattice points to your sum. So that's how the Walk-Crossing is taken into account in these generating functions. Now so this is an indefinite lattice for rank 2 with signature 1, B2. It's the other way around. It's B2 minus 1, 1. And if you continue this program to r is equal to 3, the indefinite lattice has signature 2 times B2 minus 2, 2. So you will you will see that you will get 2 of these conditions, and which will then make sure that you still are summing over a positive cone in this indefinite lattice. But yeah, it is a lot more complicated. Okay, so let me then just in words say you something about the blow-up formula. The blow-up formula is basically if you have a surface S, which is a blow-up of another surface S, that these generating functions for any rank are just related by some kind of theta function. So once you have the generating function for the Hitzbrook surfaces, you know them also for all the blow-ups. Now the last little topic will be the modular properties of these generating functions. Modularity. So for r is equal to 1, we had a modular form on the nose. So that's yeah, there's not much to discuss here. For r is equal to 2, we get these indefinite theta functions, and because they are just partial sums over the lattice, they have in general not good transformation properties. And their transformation properties were just finally understood in the work of Sander Zwegers around the year 2000. And he explains how to add a non-holomorphic term, which is actually a subleading term to this generating function, with such that you get a modular, such that it transforms as a modular form. Modular form. So that's that is good for is in some sense confirming S-duality. Another nice aspect I find of this, I won't give the explicit expression for the non-holomorphic term because it's a bit technical, but the nice aspect it is that the discontinuities of the Walk-Crossing formula disappear, so that the generating the functions generating functions are continuous in J.
Yeah. What's the interpretation of this term that you need to add? I mean, in the sense you add it to make the thing modular, but how do you interpret it in terms of the original field theory?
So this is associated in the literature to so-called reducible connections. That if you have like an SU2 field, if you're studying U2 instantons, that that term would correspond to terms where A is just block diagonal. But I think it is poorly understood, actually. And so there are also discussions of a holomorphic anomaly, which explain that if you write down the total partition function Z, where you also sum over C1 over say for rank 2, and you act with a certain differential operator, then you get on the right hand side Z1 squared. But this works for P2, for example, where you don't have Walk-Crossing because the Kähler cone is just one-dimensional. But I have analyzed this for higher dimensional Kähler cones, and then you get an additional ugly term, which disappears for J is equal to minus Ks. So yeah, I think the best properties are for J is equal to minus Ks, but I find, I think it is certainly not understood from a path integral or so.
I mean, you sort of see what I'm saying. I mean, in the sense that you say this is a confirmation of S duality, but there's something you're adding.
Yeah,
doesn't seem to be part of the field theory. Well, I mean,
it is ad hoc. It is put there by hand, and it is not.
It'd be nice to see in terms of.
Is the instantine moduli space compact?
It is compactified. Yes, but it is not it is compactified at many levels. One level, it is going to sheaves is a compactification because then you allow point-like instantons. But then the moduli space of semi-stable sheaves is not compact, and then people compactify that space. So
What about these reducible connections? Do they occur in some sense at some boundary of moduli space or something?
yeah, that would be a boundary of moduli space.
Comments related to both of these. So the partition function you wrote down for r equal to 2 had a 1 over theta.
Yeah.
You erased it. It was 1 over theta tau comma 2.
Mm-hmm.
So that sort of shows that there must be some non-compactness when z goes to 0. In some effective theory, whatever it is. And generically, when you have such non-compactness, you have continuum in the spectrum. And once you have a continuum, you have to make a good definition of a density of states. And now the difference between bosons and fermions might not be the same, unlike in a compact theory where you have a minus 1 to the f. And quite generically, that kind of a mechanism gives rise to a non-holomorphism.
But yeah, this is different because the Euler numbers are just given by 1 over eta to some power.
But
So
not in the
somehow I'm using a trick by introducing W to do the computation.
Yeah, so that's what I'm saying. In some effective theory, there must be a non-compactness. It might not be this, right?
But yeah,
One must be able to interpret it in
yeah,
terms
one
of
would
that.
think indeed about the non-compactness to explain this.
In the mathematics, is there a unique way of making these modular spaces compact?
No, I think there are different names attributed to different compactifications. Yes.
And which one is supposedly used here?
This is what is called the Gieseker-Maruyama school classification. But yeah, currently the language is really in terms of stacks and automorphisms. And I think this kind of resembles maybe more quantum physics than actually modelized spaces. And I think actually that, if this modelized space has singularities, that what these generating functions are computing is the so-called intersection cohomology. So it is the cohomology outside of the singularities. You don't take that into account. Okay, so this is basically what time allows to say about the rank 2. And for rank 3, this is work in progress with Kevin Brinkman and Sander Zwekers, how to the precise modular properties, which are a lot more intricate. So it will be hard to explain, I think, from a field theory perspective, what non-holomorphic term is. But
it's not modular. You don't get some vector value modular guy or something.
no, it is. Somehow your shadows get uglier. Somehow it is like your shadow is again mock, and it gets. You get somehow deeper into the so somehow the
What's a shadow?
okay, there's okay.
This is too far off.
It's not so far. You have a holomorphic modular form, say f, or you have a holomorphic generating function f of tau, which does not transform completely modular. Now you add something which is essentially an integral from tau bar to I infinity, and now you have a function g here. So let's say this is tau minus sigma d sigma, and there might be some power in tau and sigma. Now if you take the tau bar derivative, okay, maybe it's like this. If you take the tau bar derivative of the whole thing, then you get something proportional to g of tau bar. That's basically the story, and this g of tau is itself a modular form. And so there is a connection between, these are not quite modular forms, but now these are good modular forms. And for these higher ranks, somehow that is not, doesn't go through. G is called the shadow. Okay, thank you for the attention.
Can Jeff ask his question now? Or have you answered it?
I guess you said that there's some understanding in terms of a holomorphic anomaly. I guess I was just wondering whether is there some field theoretic argument involving anomalies that you could use to predict these more complicated modular properties for higher rank without doing the computation?
No, I don't know. I know a setup where for half K3, which is embedded in a local calabial, and then people have computed the periods, and then you can use the T-duality on the elliptic fiber of the elliptic surface. The half K3 is an elliptic surface, and in that case you map basically Gromov-Witten theory to this D4 brane theory for any rank, and then you get a prediction actually, and then that works for higher. But it is not the D4 brane. There are not D4 brane arguments that give the non-holomorphic part. In that case, it's our periods that give the non-holomorphic part.
What modular form do you get for rank 2 on half K3?
On half K3, actually, this reduces to the second Eisenstein series. So there is not really more.
Trivial Mach modular form.
It is more simple as a Mach modular form. But you can see that if you do this for certain lattices and go to a certain limit, that the kind of the Mach modularity becomes just the second Eisenstein Mach modularity.
Any other questions? All right. Everyone's hungry? Thank you very much.
Very good.